I have a few.
Please, Emil.
Thank you very much for this very interesting talk. Okay, first question will be about this transition soliton or a domain wall soliton. And you show, for example, this 3D structure where we go from one state to the other one. If you can put that one again.
This one? Or?
No, it was like a tube.
Ah, yes. This one's also movie. Yeah, maybe this one.
So yes, this one. This will be a fantastic toy, for example, for kids to you 3D print it, you can mass produce. The only problem is, how do you go back to the original state?
So this is the point I did not discuss. So to go back, transition waves are actually one-way waves, and that's done. You do it once, and this is done. You have to reset the sample by hand, let's say, by pulling on it and putting it back to the extended state, stable state, actually. So this is a case where, for instance, when you play with this, you have to do it by hand once the wave is triggered.
Yeah. So you mean on that 3D tube, if I pull, it will elongate, but it will also change its width?
So I guess, yes, the width will be changed. As you can see here, these are like auxetic materials. So when you pull on them, they also extend and so on. But so the tube, I would, I see, it could still be, I think, a good toy for children. So you would push on it a bit. It will shrink.
Yes, that's right.
Speeds and so on, or even different movements. We can program that. But then to reset it, you need to pull it again and put it again in the stable state, which is extended.
So it will work.
Yeah,
you can do it again and again.
Yeah, as a toy, it will work, I guess.
Also, for example, in this simulation, if the system will be infinitely long, then this will have to move an immense amount of mass. So it will not, I'm not sure even how one will simulate such a system in the presumably infinite.
Yes. This is a good, very good question that shows that you got the physics of this. So if you look at this example, for instance,
yeah, that's right, exactly.
The whole part of the sample is moving, is dragged with the transition wave, because this is heavier or more sticky to the surface, let's say. So this is this part going this way, and at the end maybe you will see part of this. Oh no, this is well attached. But so the sample has moved actually, and if it's infinitely long, it's true that the friction will be infinitely large, and this means that the wave cannot be triggered, let's say. So this wave is actually possible in finite systems. An infinite system with friction would not work, or you have to remove friction.
But even if you remove friction, you will still have to move an immense amount of mass. So it will not work even in vacuum, or it will be very slow. Or
yes, so this is something that can work with finite systems.
Maybe one more question, and then I let the other people ask questions. It seems that a crucial element here was the interplay between translation and rotation. And we were toying with systems which have only rotation, like spinners, which the center of mass fixed. Do you think such soliton solutions will not be possible if you pin down for example, the center of these squares?
So definitely the solutions we found would not be possible because they involve the coupling between the two components. However, if I can go back to the equations of the very beginning. Here, maybe.
That's right, because I'm thinking with some design, I can always design such a coupling equation. There is nothing to prevent me to actually design such a coupling.
So actually, this this chain of coupled pendula, when you don't limit yourself to small amplitudes, they can support solitons, but they won't be any more vector solitons. They will be purely rotational solitons. But yes, so I guess depending on the system, it's also possible with only rotation to get solitons. The only problem is that, I mean, let's say the step forward that is made between these mechanical systems that are like very interesting for many studies and highly nonlinear and so on, is that these are not really materials. I mean, these are elements, mechanical elements that are put together. So they need a support and so on. While when we go to systems like I presented, the rotating square structures, for instance, these are really like materials you can handle and bring somewhere, put in there in some structures to attenuate sound, for instance, or vibrations. This makes the big difference, I would say. Yeah. And in this case, pure rotations are very hard to get when you don't pin or support the rotators, pendula to something. It's hard to get a pure rotation, I guess.
Yes, we are mostly interested in information, transmission of information. So in that case, we don't need support or so not mechanical properties, but rather information transfer. Now, when you put this pendulum here, I will guess they are coupled through the torsion in the beam or something like that, which...
Yeah, this was just an analogy actually to show that this part of the equation, forgetting about these terms, is equivalent to this problem of pendula that are rotating like this and that are coupled to the neighbors with torsion. Yes.
Torsion, exactly. So then that will also prevent, I mean, you cannot go around and around because you'll break that.
Yeah, in principle it's possible, but yeah, and you go to topological solitons, but yeah, I mean there are like like examples of that. Like this one is exactly the thing.
Yes. Thank you.
Okay, thank you.
Hello, can I ask a question?
Sure, Oliver.
Sure.
Yeah. When you showed your last slide, I immediately thought of the applications in biology. And have you thought about the way worms move? Worms, earthworms. Are they the same mechanics? Has anybody ever considered that?
So actually,
the equation of a worm. Can you?
Yeah.
Yeah.
Oliver, you may laugh, but we have looked through the literature when we studied that. So this is actually a study which we published last year on the locomotion using a slinky and solitons, rarefaction soliton propagating in there. So the thing is, a worm doesn't move like that. There is most of worms, there is a central part which goes up, which shrinks like that, and then this type of this bump on the worm is like moving because no friction.
You're talking about caterpillars. You're right, but earthworms, they don't go laterally; they only go longitudinally. So I thought it was like you're splitting.
And they are not auxetic, which means that when they are elongated, they shrink also like this. So this is the same process, I would say. Like you remove friction in some part of the worm.
Have you ever thought of coupling several live earthworms together and watching how they move in a humane way.
Not yet. These are animals. I don't hurt animals.
Okay. Well, I thought you could have a long chain of worms and see how they move. All right. Thank you very much. Yeah.
You're welcome.
Yeah.
I have a question also. Yeah. This is Albert Sanchez from Barcelona. Very interesting talk. I really enjoy. I think all the animation and so on were very interesting, and the physics involved. I have a question concerning the squares when you mentioned that, because I mean you show that there is a gap in the amplitude. Then you could demonstrate a diode effect. So if you make an analogy with semiconductors, the next thing that comes to mind is a transistor. And I wonder whether you have thought about that, or it is something possible, because it looks like all the ingredients could be there, right? I mean, you could control some kind of one of these mechanical wave with another one made of solitons or not. And you have the intrinsic nonlinearity that you need for that, right? Because if this makes sense, maybe it would also make sense to make with this, for example, logical gates or something to make some kind of mechanical computation. Does this make sense? Have you been exploring along these lines?
So I must confess, this is something we thought about, because as soon as you go for a diode, for instance, you start digging into this direction, right? So this is something we thought of, but did not really work on. So I think it's very relevant what you say, that once you have a diode, you can build a transistor controlling the passing character or not of the diode and so on. Mm-hmm. This is a very interesting direction, I think. Yeah, very nice. But we haven't done anything on that. Yeah. I mean, in this context, because we've done things in acoustics, but so in this context, the only problem I could see, if I don't like to see problems before very nice outputs, but the only problem I see is that this is a diode for pulses, for solitons, and when you think of transistor, for instance, you would think that you need to make it pass or not with the control with the gate with a let's say a fully controllable manner, like a switch on or off, and this would require maybe to send many pulses all the time, and to have an information on passing through the transistor, which is a bit cut. I don't see a way that with pulses you can actually control and make it passing or not the transistor.
I see. Probably you're right, but still, for example, I don't know if to make, for example, simple logical gates that you can, maybe this context of pulses would somehow work in the sense that you have something like digital processing, say, but kind of mixing between analog and digital, mechanical and so on. Well, I don't know. Maybe it would be a good way to explore. So
I think the very nice strategy probably could be to mix these bistable systems and these nonlinear propagating systems.
Yes.
We've shown actually recently, it's unpublished, but we've shown that it's possible to trigger a transition wave with a soliton. So a propagating wave will trigger a transition wave in a bistable system, and so on. So this could be an idea. Of course, bistable systems have to be reset also after the switch.
Yeah. Thank you. Very nice work. Thank you.
Thank you.
Yeah. So
can I ask another question? One more. It's okay. I have a question about analogies of your work in electromagnetism, and secondly, more difficult, in gravitation. Could you comment on those two cases, if the analogy exists or not?
there are analogies, like for instance, vector solitons are have been observed in optics. So these objects exist in other types other types of waves, but apart from that, I don't see many analogies. The processes are very different from these rotating square units here to the birefringence of in optics. The concepts are very different, so I don't see much analogy.
Thinking of a line of planets or something, or a line of black holes or something like that in gravitational physics.
Yeah.
Not very easy to do an experiment, but
I don't see any like ordered organization of planets or black holes coming anytime soon to test that. But okay, let me think of it.
all right. Stimulating.
The stupid answer soon.
Okay, thank you.
Since we are on at this slide, can I ask a quick question?
Yes, sure.
You showed movies, but the excitation was always in the same way, that you're pushing with just one pin, and you can also push with 2 pins. What happens when you push with 1 pin from this side and 2 pins?
Yes. So this is there.
That's right. So here, for example, this is reflection of the solitons. How if you do the same thing for the diode? Will it depend how you excite?
Yes, exactly. You've got the point. So here, if we excite with in the middle like that, so it induces a rotation in the, let's say, plus direction here, and there is a soliton propagating all the way through. If we excite with this different impactor, the rotation will be in the other direction, and there will be the same type soliton, let's say, where you cannot distinguish it except from the direction of rotation going through. Mm-hmm. But it's clear that if you, for instance, excite the other rotation here from the left, it will be reflected by that. It will be the other soliton solution. And if you excite also the right soliton with a positive amplitude from the right, you will go through. So these systems is actually working if you excite the same way on both sides.
Both sides.
So it's even more versatile that we think of. But okay,
yeah.
you have this diode, and you have an impactor and plate, something like that, so that you cannot excite anything else than that. Any pulse will be transmitted from the left to right, and any pulse, if you excite also with the well-designed impactor, will be stopped. But it's true that you can do vice versa. You can expect also different solitons.
So that makes it more interesting, in my opinion.
Even more versatile. Yeah.
Versatile,
right.
Yes.
Yeah.
I am surprised that this Lego construction and plastic thin plastic plates, it works so well.
Yes, it's
amazing.
Rather amazing, actually. So for pulses, you could see the very simple way.
This is absolutely amazing.
Very robust. So one problem is that on the free end, you don't really know what's happening, and the reflection is not very clean, and so on. So it works for let's say the right-going soliton here. And there is no perfect conditions to actually make it reflected, make it reflect on the boundary. But yeah, it works very well. It's amazing. The problems we had, maybe I can just show that, is when we go to some finite systems that we excite with periodic excitations. After a while, let's say hours and hours of excitations, the plastic shims they start to plastically deform and break eventually. So this is a more challenging configuration actually when you excite periodic waves in there.
And can you set standing waves in this solitonic standing waves?
You mean in these systems, like having like resonances and so on?
So if you continue generating pulses, and if they will reflect perfectly, will they set a standing wave in any?
Yes, if the repetition rate is actually right one, corresponding to a resonance, for instance, it would work. I would say we haven't tried that.
Or maybe even pulsing it from the both sides to set standing waves. This will be huge standing. I mean, this will be huge deformations. Not
yes. Actually, this is the thing that is behind this. When you excite sine with periodic excitation here at the resonance of a system, you get a huge static displacement. On average, the structure is shrinked, so that imagine you put hundreds of unit cells, it will shrink by probably you excite an amplitude which is less than a unit cell size, and at the end of the system you have a displacement, a shrinking, that is 10 unit cells, for instance, in static on average. So you have oscillations around that, but you can really shrink it. So this is what we are actually investigating currently in this.
Can I ask one question?
Sure.
If you go back to the first section when you start talking about the nonlinear Klein-Gordon, I might be wrong on this, but I thought the Klein-Gordon didn't have the Setch solution, and I would expect breathers rather than a real soliton immediately from this.
So yes. So the thing is, we go to a nonlinear Klein-Gordon equation which has this shape, but there is a tiny difference from the usual one. First, the operator is on a single variable, which is the traveling wave variable. But I mean, if this is let's say a nonlinear equation, a partial differential equation. But if you take the solutions to that, you get, I mean, in textbooks and so on, you get directly to that. So for the quadratic nonlinearity, it's a t parabolic second square. For the cubic nonlinearity only, it's a t parabolic second. And for the quadratic plus cubic nonlinearity, it's another wave, another solution again, which is different. This one. So in this form. So you have like standard solutions in the form of solitons for these equations actually.
Okay.
Does it answer the question? Maybe not.
Yeah, because even in the textbook, I looked it up before because I wanted to check. They don't have this as an exact solution for it, which I thought is very strange. So yeah, that's the basic question. Is this really the exact solution, or was this something?
No, these are the exact solutions.
Okay.
If you are interested, I can give you some references on that. There are even like exact solutions for higher order terms here, up to probably the 6th order or something like that.
Yeah, I mean, because the textbook I have doesn't give these solutions, so it'd be nice if you could give me a reference on that. Yeah, thanks. All right.
Okay, is there any other question?
Okay,
I have a very quick one.
One more silly question. Sorry about the silly question.
Please, Oliver.
Third one.
Well, every time it gets more difficult. So these days it's very cool to do metamaterials, and smart metamaterials is cooler than passive metamaterials. So you're only a passive guy, so you're not so smart. So what if you smarten up your research a bit and stick in energy supply in each unit cell, and then you've got so many more degrees of freedom, you can program your metamaterials unit cells. And if you combine the smartness with the non-linearity and all the rest, what is it you can't do? I don't think anybody usually asks what you can't do, but what is it that can't be done in this field? Or you're going to tell us you can do anything at all if you have that flexibility?
I guess the limits to that are connected to our imagination, right? I mean, I feel sometimes limited by what I can think of, even with these passive dump structures. But let me go to this final slide where I evoke some prospects. I mean, colleagues like Jordan Rane, we collaborate. I collaborate with. They go already to even smarter materials, possessing, for instance, magnets in there. You could think of controlling the magnets using electromagnets and so on to control the bistability of the systems, to reconfigure them also with other waves. I mean, going smart is not necessarily a direction I would take myself, because it requires energy, right? And we are in a world where we want to economize energy. And I'm with this, for instance, this example, I'm more like programming the architecture, the matter, in order to get very complex effects from very simple excitation. And the idea here, for instance, is to excite a sine wave. And a sine wave is something easy to excite usually. And just by, let's say, controlling its frequency and its amplitude, so 2 parameters, the matter does the rest, the system, the metamaterials does the rest. It will go to very complex movements that can be predicted, for instance. So the complexity is in the passive and the complex architecture, and the number of complex movements you can do, or actions you can do, or effects, is just controlled by 2 simple parameters like frequency and amplitude. So I would better go to that, let's say. But this is probably my my profile. I don't know, my sensitivity, which pushes me to that, rather than using smarter and smarter microprocessors, maybe inside the material and so on, or actuators, hundreds of actuators in the nanorobots and so on, if you go crazy.
I'm glad you answered the question like that. I agree with you. I agree with you, actually. Most people agree. I think the best papers are published on systems which do it themselves, not which are artificially. That's the way things are going, but that's just a question of art rather than science, in a way. It's a question of minimalism, isn't it? Minimalist research is always more highly evaluated than something too complicated or too expensive. Isn't that right?
You call it smart way, but I'll call it brute force, because you just
yeah, they should call them brute materials, not smart materials. We should start a new trend to call them brute materials.
We try once, and you end up with let's say hundreds of wires coming in. You have to program them. It's just an impossible task to synchronize all of them. So the technology, what you think it is there, but it's not. If you need to synchronize them up to milliseconds or something like that, you simply cannot do.
I'm glad somebody said that. Anyway, yeah. Okay, thank you.
So looking over the slides was very interesting. So you started with these soft materials. Soft material, you try you were forced to put these masses to see a wave propagation. At the end of the slide, you moved on to how you will call these materials.
You mean this one?
So this is the soft material, and at the end, you abandoned this and you went to more rigid ones, or how you call hard.
Yes, actually, this 3D printing is PDMS. It's a single material, so the geometry makes it soft when it's thin and more rigid when it's bulk, let's say, in the middle of the mass. But at the end, it's quite stiff. This thing, and the Legos are actually much softer when you compress them and so on. Very, very soft, but also very lighter. So the waves travel at similar velocities, I would say.
So will you go back to this soft system made out of PP, these polymers?
Yeah, I think that's what historically we started with that, and the thing is, it's the process to go to that is much more demanding, very hard to 3D print this. But at the same time, you can really 3D print anything. I mean,
that's right.
While using Legos, for instance, you have only a few number of different pieces that you can run together and so on. Even if you can tune the elasticity by changing the film thickness or the length or the height and so on, but this would allow, for instance, to print 3D materials that are like this, and showing the same rotating mass characters and so on. So I would say it's these samples are more, let's say, close to the application than the Lego structures that are more for highlighting effects and playing easily with the parameters by changing the Lego pieces and things like that, or returning the system and so on. So yeah, we started by the end. Actually, this could be our, let's say, last sample showing this, and maybe this could be put in some shoes or other, I mean, practical objects, but not the Legos. Yeah, definitely.
So you have to go back in one way.
Yes, I have to stick with Jordan money for some few more years, and I condemn to work with him, which is a great pleasure.
Could I just ask a very quick question, if I may, please?
Sure.
Yeah, I'm Marcus Wheel from the University of Strathclyde in Glasgow. I noticed that some of the materials you've been studying are based on these rotating square auxetic type family of materials. But another major class of auxetics, of course, is those that are based on reentrant polygons of beams connected together. And I wondered whether you'd considered looking at this class of material, because they also operate by a combination of large rotation and translation, don't they?
Yeah, that's right. That's a good idea. I mean, this is part of the systems we could we could think of studying. I could add them somewhere here. Ensemble of beams, for instance, that can buckle, and so yes, I mean, even following the seminal work of Lakes and so on, but yeah, probably this would not change much, I would say, in the modeling and so on. Let's say the favorable configuration we have here is that we can really separate rigid masses and springs. So making a lump model out of it is a kind of, let's say, straightforward. while with these reentrant beams, buckling, and so on, it's probably a bit harder to have a very simple model directly modeling this. I mean,
yeah, but you might, for instance, be able to fabricate something out of Lego again relatively straightforwardly.
You're right. Yeah, that's a really nice idea to look into this direction, especially because I think of the possibility to go 3D with that. Quite. Yes. I mean, in statics they have been worked so yeah, nice.
Not sure.
We should stop here for today. Obviously, if you have any other questions, you can contact Vincent by email.
Yes, don't hesitate. Yeah.
Okay, let's thanks again, Vincent, for this interesting talk and his answers. And see you next week when we have Angela Madeo from Institut National des Sciences Appliquées de Lyon, in France. And yeah, stay safe. Thank you.
Thanks.
Thank you.
Thank you all. Bye.
Thank you.
Thank you.